Hello and welcome back. This is the first of three videos for Chapter 12. Now, in Chapter 12, um, we learn about the origin of the magnetic field, starting off with current flow. But before we get into that, what I'd like to do is to talk a little bit about the magnetic field itself. And we're going to see this as this chapter and future chapters go on. The first thing I'd like to point out is the fact that the magnetic field itself is not a conservative field in general. So in general, it's not conservative. Now, as a consequence of this, it doesn't experience many of the benefits that we do when we deal with the electric field. For example, the fact that the electric field is conservative means that we can do things like express the electric field as minus the gradient of some sort of electric potential. Okay, we can use things like Gauss's law to simplify calculations as long as we can exploit symmetry. So, because it's not a conservative field, we can't do things like this. We can, though, appeal to a theorem called Stokes' theorem, which will allow us to relate the properties of the magnetic field to current flow. But it's not the same thing as Gauss's law, and when we get to that point, we'll discuss why. That said, what I would also like to point out is that much like the relationship between the electric force, charge, and the electric field, sort of as being an experimental relationship, hence Coulomb's law being an experimental, law. The law that we're going to begin talking about now is also an experimental law. Now, this is called the Biot-Savart law. It's named after two French mathematicians and physicists. And what they discovered was that if you have a wire, a loop that has current moving through it, as a consequence, there's a magnetic field generated. And this magnetic field has some relatively complicated properties. It's not nice like the electric field is. As we saw, the magnetic force is a lot different than the electric force. And it's a differential law, and it looks like this. That's mu naught over 4 pi, and I'm going to get to what mu naught is here in a moment. I dl vector cross r hat over r squared. This is one form. This is the form that your book uses. The form that I prefer to use, which I will be using in this video and future videos, is this one right here. It looks a lot like the other one, except it's a little bit more generalized. And we've seen something that looks like this when we talked about Coulomb's law and the electric field as well. So let's talk about mu naught. Now, if you remember in our discussion of electricity, we talked about something called epsilon naught, which was the permittivity of free space. Mu naught occupies a similar position as epsilon naught does, except with respect to magnetic fields. It's a constant as well. We call it the permeability of free space. Permeability. And it has the value of 4 pi times 10 to the minus 7th Tesla meters per ampere. Now, let's talk a little bit more about the Biot-Savart law, specifically how to visualize it. So, let's write it here. Like I said, I like the more generalized version. So we're going to use that. right there. And so I want you to imagine a wire or a line of current. Maybe it goes like that, we'll say through space. Flowing this way, right there. Now let's draw the origin of a coordinate system. How about right here? We'll draw a full three-dimensional one like that. This is Z. This is Y. This is X. Now, let's pretend that I'm interested in the magnetic field at that point in space. So relative to the center of our origin, that's my point of interest. So that would be R. Now, this magnetic field at this point is a consequence of this current at all points along here contributing part of a magnetic field to that. So we're going to look at a small little bit of current, which I'll call DI. Okay? And DI has the value of I times DL. The units aren't exactly right, but this is what we're going to run with. Okay? Now, so this right here, actually let's the magnetic field at this point is a consequence of all the little bits of magnetic field contributed by current along the entire path. That contribution we think of as being due to a small little bit of current, which you could think of as sort of as a DI. But this current is constant right here. This is the assumption that we're going to be making for quite some time. So dl vector is in the direction of the current itself, and that's what we're integrating over. Now, R prime locates that little bit of current relative to the origin. Now this right here would be the direction from the bit of current that we're looking at to the point in space that we're interested in. And if you think of this as R, and this is R prime, this naturally would be R minus R prime. The way to think about it is that R prime plus this equals this. If you do the math, this is what you get. Okay? So, that covers all the things that make this up. So, knowing this, let's do an example. This is an infinite line of constant current. We'll say it moves from left to right along the z-axis. So this is the direction of I. And this is also the direction of dl vector, just for reference. What I'd like to do is to work this problem twice. We're going to do it once in Cartesian coordinates at a point rather, that is d above the x-axis. And then we're going to make it a little bit more general. And you can see that you get the same solution in both cases. You just switch unit vectors a little bit. Okay, so the first time, like I said, we're going to do it in Cartesian. Then we're going to do circular polar coordinates, specifically cylindrical coordinates. All right. So here is our little bit of current right there, we'll say. This right here locates that bit of current with respect to the origin. So that would be R prime. And you notice how it's along the Z axis, like that. So your current is located from minus infinity to plus infinity all along the Z prime axis or the Z axis. This right here is the point in question that we're interested in. Right there. This would be R. R is D above the x-hat axis. This right here is going to be R minus R prime. R minus R prime is exactly that. It's R minus R prime. Okay, so now we pretty much have everything that we need to plug into the Biot-Savart law. Okay, so next up, let's do the integral. So if I plug in the stuff that I have, and I'm just going to sort of lay it out right here, this is what my Biot-Savart is going to look like, or law is going to look like. I is constant, so I'm just going to go ahead and pull that out. dl here, if you look at it, is going to be dz z hat. R minus R prime is this right here. In the denominator, we have the length of R minus R prime cubed. The length is the square root of the sum of the sides. That's the square root, or that's the sum of the sides squared. The square root to the 1/2 power, you cube that. So that's what you have in the denominator. Okay? So this is basically mirroring everything that we saw when we did the electric field or the electric force in their differential forms, with the exception of the cross product that's sitting there. And we're about to handle the cross product now. So the way to handle the cross product here is to break it up into two pieces. You have one piece that deals with z hat cross x hat, and then you have another piece that deals with z hat cross z hat. So piece number one, and I'm just going to write it over here, is going to look something like dz prime z hat cross d times x hat, d being the distance above. The second part is going to look like dz prime z hat cross a minus z prime z hat. So let's address the second one to begin with. And the vector parts that end up being crossed are z hat and z hat. These are the things that you can't pull out of our cross product here. And any vector crossed with itself is equal to 0. So that part doesn't matter. It doesn't contribute. On the other hand, you have this z hat cross x hat that we have to do. And the way I do that, I've mentioned before, is to draw a little three-dimensional coordinate system like that. Z, y, and x. And then put my fingers in the direction of z, close them towards x, and my thumb points right down y. So what that tells me is that z hat cross x hat is equal to y hat. So that allows me to do the cross product. So at the end of the day, all this stuff here that I'm crossing at the top really only boils down to this. And when you do it, you end up with dz prime times d times y hat. So that's what this is right here. The d is, again, the height above the x-axis, so it's a constant. So I'm just going to pull it out here. D times I. The y hat is also constant. That comes out as well. And then what I'm left with is, at least, stuff that's relevant that we're going to ultimately end up integrating over, is going to be dz prime divided by d squared plus z prime squared raised to the 3/2 power. So this is going to be what we're going to end up integrating over from minus infinity to plus infinity. So if I go ahead and put an integral on this, the first thing we see is that on the left-hand side, that turns into just the magnetic field as a function of position. I'm going to put that as r for right now. And on the right-hand side, like I said, you have a whole bunch of constant stuff. Mu naught is a constant, I is a constant, d is a constant. Y hat's a constant, 4 pi, constant as well. And you're integrating from minus infinity to plus infinity of dz prime over d squared plus z prime squared raised to the 3/2 power. Now, what we're going to do here is a substitution. This is a substitution that we've done a number of times in the past. What I'd like to do is to call z prime equal to d times tangent of theta. So dz prime would equal to d is a constant, d times secant squared of theta d theta. Now if I look at how my limits here work, we're dealing with a tangent here. And we know tangent's kind of funny. When you plot it, this is just sort of a rough sketch, it has this shape like that, where it's asymptotic here and here. On the negative side, where it blows up to negative infinity, theta would equal to minus pi over 2. And over here, where it goes to positive infinity, that's where theta is equal to pi over 2. So now we know what our limits of integration is going to be like. Okay. So let's go ahead and plug in our substitution. You have a mu naught I d y hat over 4 pi, the left-hand side of the integrand. Here, we're going from minus pi over 2 to pi over 2. dz now becomes d times secant squared of theta d theta. In the denominator, we have a d squared plus, now we have a z prime squared. Z prime is d tangent of theta, so you're going to square that. That's going to be d squared tangent squared of theta raised to the 3/2 power. And what you can see here is that at the top you have another d, which comes out and makes this d squared. But in the bottom, you have a d squared. When you pull that out, it is raised to the 3/2 power. So the half is going to kill the square, but then you cube it. So you'll have a d squared on the top, you'll have a d cubed on the bottom, which means that that ends up being a 1 over d. And so to rewrite that, that's what you have sitting out in front of the integral. You have a secant squared theta d theta. You have a 1 plus tangent squared theta raised to the 3/2 power. And now let's talk about this. So, so this right here is a trig identity, right? Because you know, secant squared minus tangent squared is equal to 1. So this is right here is just secant squared theta. So when you take secant squared theta and raise it to the 3/2 power, that becomes secant cubed. Here you have secant squared on the top. So this is 1 over secant theta. But the thing is that secant theta is equal to 1 over cosine of theta. So this is actually just 1 over cosine of theta, which means that this is just cosine of theta. So our magnetic field as a function of r is going to equal to mu naught I times y over 4 pi d times the integral from minus pi over 2 to pi over 2 of cosine of theta d theta. Now, the derivative of sine is cosine, so the integral of cosine is sine. So when you do this integral right here, this is mu naught I times y hat over 4 pi d sine of theta evaluated from minus pi over 2 to pi over 2. Well, this right here is pretty easy because sine of pi over 2 is 1, and then sine of minus pi over 2 is a minus 1, which means that that is really just 2. So this is a 2. You have a 4 here. That's going to kill that off and make that a 2, which means our magnetic field as a function of position in the following problem is mu naught I y hat over 2 pi times d. So let's copy that and come up over here and take a look at the picture again and see what that means. So at this point in space, because we're just looking this high above only the x-axis, okay, so we're only along the x-axis right here. At this point in space, the magnetic field depends upon how far along the x direction I am, but it points straight out of the board at us. It points along the y-axis. Okay, so here it would be pointing straight out at us. So this would be the direction of B at this point. Now what if I were to work exactly the same problem and put that along the y? Okay, so let's pretend that I worked the same problem here. I was d away from the y-axis and I wanted to know what the magnetic field looked like. Well, all the stuff here would be the same, with the exception of r. My r vector, which locates the point that I'm interested in, would, instead of being, dx hat, now it's going to equal to d times y hat. So if I put that in here, just like what we had done before, you would end up doing this cross product right here, which would be z hat cross y hat now. And if you use your little sort of easy cheat here for doing that, you put your fingers in the direction of z, you close them towards y, and what you have is a thumb that points down the negative x direction. The calculations would be exactly the same. So at this point, the strength of your magnetic field would be the same, except it would be pointing straight down the x direction like that. Now, if you were to repeat that for, say, minus x, or minus d rather, below the x direction, what happens is you get a change in sign. At this point right here, d below, your magnetic field would be in. It would have the same magnitude as it does here and the same magnitude as it does here. And if you were to look into the screen this way and do the calculation, you would have that it points straight up the x-axis. So at the end of the day, were you to look sort of with a front view, doing a bunch of calculations like that, you would have your current coming straight out at you like that. So here's your current. This would be straight. This would be the z-axis coming straight at you. So z is looking like that. You would have this would be in the direction of x, and this would be in the direction of y. And your magnetic field would look like this. It would form a closed loop centered on where the current is. You would have coming out of the screen here, going down the x-axis here, going this way, and going this way. So, at the end of the day, what you have is a magnetic field that forms a closed loop centered on the current, and it has this direction right here. It's circular like that. Now, so obviously we solved this one right here for just a point in space. So how do you express this in a more general form? For example, what if you're a distance of r away and you're in the xy plane, or you're just looking at r away? Because as we saw here, the z parts actually cancel each other out, much like arguments that we made with respect to the electric field, except a little bit more complicated because of the properties of the magnetic field. So how would you express this? Well, in general, for a long straight line of current, we say that your magnetic field, as a function of r, is mu naught I over 2 pi r, r hat, or sometimes rho hat, depending upon how you want to express it. R hat being in the direction of radially outwards away from the line of current right here, but straight away from it. So not at a weird angle like that. Now, were you to do this problem again, for a more generalized way of writing this, what we would say would be the following. For a long line of current, we would say that your magnetic field, as a function of r, looks like mu naught I over 2 pi r theta hat. Now, theta hat means in the direction of from x towards y along a circular arc. So we've seen this before. This is sort of a manifestation of circular polar coordinates or cylindrical polar coordinates as well. So if I were to go back over here and look right here, if you were to think of, again, this as being the z direction, this as being the x direction like this as being the y direction like that, then what you have is a circular magnetic field like this. In cylindrical coordinates, you could think of this is technically rho in cylindrical coordinates right there. That is in the rho hat direction, outwards radially in the x, y plane. At right angles to that, you have theta hat. And then at right angles to those, you have z hat. Now, I encourage you to try doing this integral again, except use these coordinates. You have to be careful, though, because rho hat and theta hat both change with position like this. So, it's one of the caveats with respect to using these types of coordinate systems. But this is the way that you would write it right here. Okay, so in this example here, what we have is a loop of constant current. The current's I. It makes a circle in the xy plane of radius r. Now, let's write down our Biot-Savart law. It is dB is equal to mu naught over 4 pi times I dl vector cross r minus r prime divided by r minus r prime cubed. Let's talk about what these are now. So we'll pick a little bit of current element right here. This is the direction of dl vector. Remember, that's always in the direction of I. We're going to talk about what that is here in a moment. This right here locates my little bit of current. So that right there would be r prime. And then the point of interest that we're looking at is right up over here. That's where it is relative to my current element. And this right here is relative to the origin of my coordinate system. So relative to the origin, you would be talking about r, which in this case is d z hat. It's d above the z-axis. So what we're doing is we're looking at what the magnetic field is along the central axis of this circle of charge. This right here is r minus r prime. Now, in order to do this, we do not want to use Cartesian coordinates. We could, but it'd be pretty complicated. Probably the best thing to do in this example is to use the cylindrical polar coordinates that I was talking about before. So let's talk about what dl prime and what r prime are going to look like in that. So r prime itself, if you look, is the same distance away from the origin, but what happens is it changes position as it goes around the circle like this. So we would say that r prime itself has a length of r, but points in the rho hat direction. Now, if you remember earlier, rho hat is in the direction of out along a radial line in the xy plane. When you put that together with the z, then you get the full vector for where something is located in cylindrical polar coordinates. But we're really not worried about that right now. So let's talk about what dl prime is. That's a little bit more complicated. dl prime is along an arc. So what you're using here is the equation for arc length. And arc length looks like this. The distance along an arc is equal to r times theta. Now here, being on a circle, r is constant. So ds here, prime, would be the same thing as dl prime. R is constant, it has that value, and the only thing on the right-hand side that can change is d theta. If you look at its direction, though, its direction is along this right here. So that is the theta hat direction. So dl vector is equal to r d theta theta hat. Just like that. I'm going to put a prime here just to be consistent. So there we go. Now we can talk about what r minus r prime is. That's going to be dz hat minus r rho hat. Now let's talk about what our unit vectors are when you cross them. Let's draw our little thing right here. Now, for circular polar stuff or cylindrical coordinates, this is z, this is rho, and this is theta. So we have our cross products over here. Before we get to that, let's go ahead and let's just set up our Biot-Savart differential. Current's constant, that comes out. This is r d theta prime in the theta hat direction, crossed with r minus r prime dz hat minus r rho hat divided by the length cubed just like that. Now, if you look at this, you know, we're integrating over an angle. And because we're integrating it over an angle, a lot of this stuff doesn't depend upon an angle. A lot of it's just constant, so we can pull it out, which is going to be very convenient for us. But we still have to address these cross products right here. And I have two. I have a theta hat cross z hat that I have to do. That's in this first term. And then I have a theta hat cross rho hat that I have to do. So if I use my little cheat thing over here and put my fingers in the direction of theta hat, close them towards z hat, that gives me rho hat. For this one right here, if I put my fingers in the direction of theta hat, cross them towards rho hat, I get a minus z hat. So my Biot-Savart law looks like this. So there's the initially constant stuff that sits out in front. I'm going to go ahead and do these cross products and plug this stuff in. When I do, I get the following. I have an r d theta prime rho hat cross z hat, or theta hat rather cross z hat, which is rho hat, minus an r squared d theta prime theta hat cross rho hat, which is minus z hat. The minus turns this into a positive and then puts a z hat right there. In the denominator, we still have d squared plus r squared raised to the 3/2 power. Okay, so this is looking pretty good. We can integrate both sides. I'd like to point out that our limits of integration, since this is around a closed loop rate like this, are going to be from theta going its initial position, we'll say is 0, and you're going to end up at 2 pi. So you're integrating over the entire loop, just from 0 to 2 pi. So one full angle. So b as a function of r would equal to two integrals. The first one, well, first of all, they both have all this sitting out in front. So the first integral is going to have, in terms of constants, an r and a d that I can pull out. We're not going to make the assumption that rho hat here is constant, and that's because it's going to change with angle. So we're going to have to take a look at this very closely when we do the integration. I'd also like to point out that you have a d squared plus r squared raised to the 3/2. That's constant. Okay, so these are all constants right here. You're going to have to integrate potentially rho hat d theta from 0 to 2 pi. So that's the first one. The second one has got a r squared. Now in this case, I have a z hat. The z hat doesn't change depending upon where you're at in your angle. How high above you are along the z-axis doesn't depend upon where you're at on the xy. Okay, so that's a constant as well. I can pull that out. Then I have all this other constant stuff that I can pull out. Raised to the 3/2 right there in the denominator. So really what you're left with integrating here with this term is just d theta from 0 to 2 pi. That's super easy. Okay, so I'm going to call this integral number 1. I'm going to call this integral number 2. And let's take a look at integral number 2 first, because that's the easiest one to do. It is from 0 to 2 pi of d theta prime. When you do this, you get theta prime evaluated from 0 to 2 pi, or just 2 pi. Super easy. Now this one's more complicated. Okay, one is a little bit more complicated. And let me show you why. We're doing this integral right here. Okay, so what exactly is rho prime? Well, in order to do this, let's just break rho prime up into unit vectors in the xy plane. So here's y, here's x, rho hat locates something in the xy plane. It makes an angle of theta. That's what we're integrating over with respect to the x-axis. If you express this in terms of unit vectors, it would be cosine of theta x hat plus sine of theta y hat. So when we do our integration, we're going to have to integrate over these. That's the reason why I didn't pull it out of the integral. So if you were to do that, and let's just look at one of them. Let's look at, I don't know, cosine. That looks interesting. 0 to 2 pi, cosine of theta prime, d theta prime. X hat and y hat are both constants. They don't change. Their directions do not change as a function of angle. But rho hat obviously does. So let's see. The derivative of sine is cosine. So the integral of cosine is sine. Just like that. And when you plug in your limits of integration, you get 0. If you do the same thing for sine, you get 0. The reason is because you're integrating a periodic thing over one period, basically. Okay. So this is something to remember, is that if you integrate cosines or sines over 0 to 2 pi by themselves, you are going to get a 0. And what that means is that the act of integrating rho hat d theta over from 0 to 2 pi gives you 0, which means that this first integral right here is 0, which means this one right here is the only one that contributes overall to our answer. So we can almost immediately write down the magnetic field. You have a mu naught I over 4 pi sitting out in front. And then what we're going to do is just to sort of attach the rest of that stuff there. Let me clear my work area out here so I can have some space to write. we have a capital R squared, a z hat. We have a d squared plus r squared raised to the 3/2 power. And then we have the value of our integral, which is 2 pi. So pi cancels. 2 cancels with one of the 2's down here. And you end up with mu naught I r squared z hat over 2 times d squared plus r squared raised to the 3/2 power. So this is something else that you can take and you can sort of place in your repertoire, if you will. Let's see, that was... Let me just sort of snipe it and put it here. Right there. So this would be d above the z-axis, with a caveat that the loop is in the xy plane. So the last thing I'd like to do is to use one of these results, specifically the one for the long line of current, and in a specific application, and that is when we talked about last video, and that's the force on a conductor in the presence of a magnetic field. Now, if you remember, it looks something like this: IL cross B for a constant current. And just to remind you, in this case, just looking at the force and not thinking about the magnetic field stuff that we talked about earlier, if you had a long straight wire with, we'll say, current flowing this way, and let's pretend that you had a magnetic field, I don't know, coming out of the screen like this. This would be the direction of L, in the same direction as current flow. B here is out. You put your fingers in the direction of L. You close them towards B. And you end up with a thumb that points down like this. So this would be the direction of F on the wire, presumably along the entire length of the wire, neglecting fringe effects. So if you go over here and you take a look at the result that we got for a long line of current, and let me just copy and paste that. What I'm going to do is to put this into this equation, specifically dealing with a situation where you have two wires that are sort of within proximity to each other. And what we're going to do is we're going to make our lives easy. We're going to assume that the wires are parallel. If they're not parallel, it gets a little bit more complicated. So here's what we have. We have two wires parallel to each other. They're separated by a distance r. Right there. I'm going to say this is wire number 1. It has current running to the right, I1. This is wire number 2. And it has current, we'll say, running to the right, I2. Like that. And I want to ask the following question. What is the force per unit length of the magnetic field, due to 1, or do 2 rather, on 1. So we're looking at the magnetic field that's being created by number 2 and how it's going to affect number 1. So the key point here is that our wires are parallel to each other. So knowing the fact that the magnetic field is going to loop around I2 like this. And in terms of direction, there's an easy way of figuring it out. If you take and you put your thumb in the direction of I2 and you wrap your fingers around towards your palm, the way that they wrap tells you the direction of the magnetic field. So behind, it goes around here, it goes around like this. At the very top, which would be the part of the field that would affect the wire, I1, it is coming out towards us. So here it's out. At the very bottom, it's going in. So this is what our magnetic field is going to look like. So what this says is that if you wanted to look, for example, at the force on wire 1, that's going to be equal to the current that's running through wire 1 times L1, which is in the direction of current 1, cross the magnetic field due to 2 at the location of 1. Okay? Now, so let's just look at this cross product for a moment. If you were to put your fingers in the direction of I1, so this right here is in the direction of L1 right here, and then close them towards B coming out, so fingers in the direction of L1, close them towards B, what you have is a force that's down like this towards 2. Oops, that's F1, sorry about that. So let's just think about magnitudes for a moment. So everything is at right angles, which means this cross product right here literally is just ILB. Okay, if you had angles here, it would be ILB times whatever the sine of the angle in between is. So in terms of magnitudes, F1 is going to equal to I1, L1, B2 is going to be mu naught I2 over 2 pi r, r being the distance between. Now what's interesting about this is that you can swap the i's around if you just divide by L on both sides to make this a force per unit length. So these are interchangeable, which means that the magnitude of the force that wire 1 here is going to experience is going to be the same amount of force per unit length that wire 2 is going to experience, which, satisfies Newton's third law. So our force per unit length here is going to be I1, I2 with a mu naught out in front divided by 2 pi r. Okay? So just as a simple example here, I want you to consider 2 wires, one that carries 20 amps, one that carries 50 amps. They're both in the same direction. If one goes in the other way, what that does is to switch the direction of the force. So for example, let's pretend I1 was going the other way. It would push them apart as opposed to pulling them apart, or pulling them together rather. And the distance separating these two is 20 centimeters. So what we're given here is that I1 is 20 amps, I2 is 50 amps. The distance is 20 centimeters, which is the same thing as 0.2 meters. And what we'd like to find here is the force felt between the wires, which is the same thing as, the force per unit length, on this one, or the force per unit length on this one, because as we talked about earlier, they're the same. So we're just looking at force per unit length. And that's what this equation right here is. So the force per unit length here is going to be mu naught I1 I2 over 2 pi times r. Right? Mu naught is 4 pi times 10 to the minus 7th Tesla meters per amp. We have 20 amps. We have 50 amps. We're going to divide by 2 pi times r. R is 0.2 meters. Four times pi times 10 to the minus 7th times 50 times 20 divided by 2 times pi times 0.2. And that is 1 times 10 to the minus 3rd newtons per meter. Right there. So, a simple example is just showing you how this works, along with some two relatively in-depth examples showing you how to find the magnetic field at a point in space, using the full-blown vector version of the equations. Now, in the next video, we're going to talk about I'm not going to say it's Gauss's law for magnetism, because there is an expression for that. I give you a very surprising result, which we'll talk about at some point, probably the video after. But we're going to talk about Stokes' theorem, and we're also going to talk about solenoids, which are coils of wire stacked on top of each other, which are incredibly useful to us. And I'll see you then.